Great. So I'd like to introduce the next speaker, Michael Halvorson from University of Alabama in Huntsville. Um, Michael is working on is leading a very interesting project called Empire that is, I would say, a great example of using of realizing the Ray's vision of ontological rigor in using agility in performing automation. So I think the Empire a framework that you will see is covering all the grounds of the Ray's vision. And I saw a demo of it, and it even looks very cool and appealing. And I cannot wait to hear about it more from Michael and to share it with the community of ontoNexus. So with that, I'd like to give the floor to Michael to give us the tutorial on the Empire framework.
Thank you very much, Maggot. I really appreciate that kind introduction. Can y'all hear me okay? Just coming in loud and clear?
Yep, sounds good.
Wonderful. Last year, when I had the privilege to speak at the ontoNexus conference, I stood up in front of everybody and asked, if you picture in your head the perfect ontology, it had all the hallmarks of well-formedness and completeness, it was integrated successfully. If you had the perfect ontology, what would it do? What would you have it do? And I've heard a lot of really excellent talks at this forum, and it's clear that everybody here gets it. Everybody here understands the power of these ontologies, what they can do, the troubles, the struggles that we face in systems engineering and discipline engineering in general for complex systems, as well as taking these ontologies, building them out iteratively in a way that is sustainable and can garner community engagement, and also to build software around them that is useful, that is distributable. Everybody here has kind of hinted around problems that I've been working on for a while, and we're going to talk about today. But it's been really inspiring to hear everybody speak on that. So I just wanted to say what a delight it was to hear people who share the same struggles that I have, and I think we have a couple folks online who also feel those. So today we are going to talk about. We built an ontology. It is by no means perfect, and we have decided what we are going to do with it. And there were a lot of questions that were answered on the way of what is the best way to use this. And so that's going to be the focus today. Is we are all obviously highly ingrained in the ontological community. We want to popularize these ontologies, but we are not embedding our ontologies deeply enough into software to make them truly useful. So today I'm going to talk about a software that is for a specific purpose. It's a broad purpose. It's very, very broad and difficult to build. But we identified the purpose and we have built an ontology around that. And the implementation structure of how we did that, that's what I think everyone to take away is take what you see, and it might be useful to you in your endeavors to build ontology into your useful software. So there's going to be two PowerPoint presentations that we'll go today, and each of those will have a demo in them, each of the software itself. We're going to lay out the problem structure, and then we're going to move into the structure, content, and function of Empire and AS themselves. So first, we're going to look at a little bit of the research questions that have motivated this. I've contextualized this into research questions specific to the ontoNexus. Then we're going to get into kind of the background of those, and then the research plan and methodology that was executed in the pursuit of creating this software. So I have been chief engineer for a satellite program for 6 years, and it has been really difficult to synergize project management and systems engineering, and I am not alone. There is this recurring problem, is particularly in aerospace, that you lay out the project timeline, you lay out your budget and everything, and then you get cost growth or cost growth due to the schedule slipping. And this is for a lot of reasons. There are new technologies. There's a lot of people involved in these projects. The supply chain structures are not simple, but sometimes, early on, the expected project and budget can be unrealistic. The technical complexity aspects of it can burgeon over time, and a lot of these programs, especially federally funded, well, at least the way it used to be, they can expect additional funding if they expect problems. And James Webb was a really interesting look at this. It was initially estimated to cost around 0.5 to 3.5 billion dollars, and ended up being 10 billion, and it had a schedule slip of about 11 years. And there was, if you look on the right, there was no one part of James Webb's budget that just dwarfed everything else. It was pretty distributed, but it was a lot of the technical challenges that made this really difficult. When they realized that they had to use beryllium instead of glass for the mirrors, then how big it was, had a lot of verification challenges. So the critical path for the schedule network ran through the telescope and the instruments for over 10 years, and that was the real problem here. And it's not just spacecraft. For the aircraft, Lockheed Martin, similar stories. First estimated in 2010, came out the initial operating capacity or capability in 2015. It was 10 years behind schedule in the 2020s. And it originally was estimated for $200 billion, and 2 years ago, its total cost was $731 billion. So same schedule slips and cost growth. And for the Space Launch System, RIP, it began in 2011, first launch 2016, but that slipped 26 times over 6 years. Originally, it was expected to be $18 billion, and then it was about 26.4. So the root cause of this, when you kind of boil it down, distill it, contextualize it, is that the system design and the project plans were not aligned. You have this project plan that is defined before the system is really architected and designed, and then once you start realizing those technical challenges and the uncertainties, that's when things start to get a little out of control, and you get these project growth or cost growth due to these schedule slips. And there were 20 NASA projects that were studied, and at the start of the phase B, the system definition phase, that schedule growth could be explained 62% of the project cost growth from the start of that phase. So it is when you start designing your systems, you start architecting and translating that into design, that you really get this misalignment of the project plan and the systems engineering. And a lot of these programs that are building these, they want to use digital engineering techniques, and ESA, at the bottom citation there, ESA had an expectation that they were going to get a 30% reduction in project execution time just by using these tools. And we found that that's not the case. So why is it that we expect to use these tools to fix this problem of misalignment, but we're not actually getting what we want to out there? So I'm asserting here in this research that the disjoint handling of that PM and SE information during this planning is a causal factor in this cost growth due to schedule slips. And that's what the ontology that we're developing is in part designed to handle. We're going to talk about some of the semantic ambiguity. We're just laying all the groundwork for the ontology so that I make sure that everyone understands the context here. Reducing the semantic ambiguity. We're going to talk about embedding the ontology tools. And then we're going to talk about the benefits that you get when you actually use these tools here. So traditionally, we have these $100 million programs, and we know that we need to do project management and systems engineering for these. And we decide collectively that we're going to handle project management in one model, and we're going to handle all of our systems engineering in one or more models. And then we're just going to commit to doing version control between those for the entirety of the project. And these project models, there's cost as well over on the left. But it's a lot of your project trackers, critical path, earned value management, team oversight, and systems engineering. You've got things like requirements and architecture, integration, behavior, verification, risk. And so you get this project model and this integrated system model. And we use in aerospace what are called socio-technical systems for these. And socio-technical systems involve human, social, organizational, and technical aspects to them. And these could be things like air traffic control systems or banking systems. They don't have to be aerospace, but we use a lot of programs that are designed to have humans project managers, system engineers, discipline engineers are all interacting with these in various ways. They correspond to an organization. They're trying to solve technical challenges. There's a variety of socio-technical systems that get used here, and many of them are SysML based. We are going to be kind of comparing, contrasting SysML work in this as well. But I'd like to introduce the phrase integrated project model here, because I needed a word to contextualize this. And this integrated project model is how I'm approaching it. You've got this set of project management information that is contained within a set of project model information. You've got your SE and your discipline engineering information that is usually contained within some integrated system model information. Now, if you put all of those together, that's when you get the integrated project model information, where you're saying that all of this is going to be contained within the same model and it's going to be related as such. There's this concept called Conway's Law, which states that if we have these socio-technical systems and we're using those socio-technical systems to realize integrated systems, well, when you have inconsistencies or logical inconsistencies or disparate information that is conflicting, and then you use that model to realize the integrated system, of course the integrated system is going to have emergent behaviors, potentially unwanted. You're going to find problems because you had logical inconsistencies within the socio-technical system models that you were using to realize the integrated systems. So they're going to propagate into the system, which is why we need to address these logical inconsistencies at the source here. And this is just a very simple example. We're all ontologists in here. This is not brand new information, but we can define these entities and we can relate them. And then within a specific aerospace instance, we can say, okay, you've got a specific system element, it owns a function, and there is a function requirement associated with those. But when you add in the project management aspect of it, it gets a little bit more complicated. You've got a system element that owns some system function. The function requirement is associated with the system element, and you've got a project team that's responsible for the system element requirements. That function requirement is verified through some verification method here that's demonstration. And because that exists, you have these work products, demonstration report, and demonstration plan that project team is also responsible for. And the arrows, the directionality of this matters, particularly in your binary predicate ontologies. So here, just exemplifying this from an aerospace perspective, it's the exact same thing, and all of these relationships have to exist, or else you're going to get that semantic ambiguity that exists, and that therein lies the problem. So if you've got that semantic ambiguity, if the function exists but there's no requirement, the stakeholders viewing the requirement spec are going to be misinformed. If the requirement exists, but there's no corresponding function, you're out of compliance. You've got a requirement specification and your system design is not compliant with that. If you've got the requirement and the function, but they're allocated to different system elements, you've got an inconsistent functional architecture and requirement specification. So all of these relationships have to exist simultaneously, and we have to infer that all of those exist in order to relate this PM and SE information. We're going to focus a little bit on SysML here because I used SysML for a good 3-4 years trying to overcome these problems, like many people in industry have, and I just wasn't getting the results that I was looking for. So we're going to look at a little bit of quote unquote shortfalls, but certainly not nothing that can be overcome with SysML. And it should be clear that all of the stuff you're going to see we're intending to export to SysML. None of this is designed to replace SysML by any means. SysML will always do things that Empire can't. But the logical inconsistency is a serious problem within SysML. So there's a lot of aerospace folks that contributed to it, and many more use it. It's extremely common. But we have these formal languages that all have syntax, or how the expression is structured, and semantics, what the expression means when it is structured that way. And there's two kinds of semantics that need to be differentiated here. There's conceptual semantics, which is semantics in the sense of meaning. We mean that the function requirement always has to have a corresponding function to it. Every system element has to have a given function, lest it be superfluous. And then there's computational semantics, and these are the ones that SysML has. These say that within a given software platform, within a given socio-technical system, that you can create specific relationships. So you can say in SysML that a requirement is satisfied by a given block. That's an allowable relationship, but it means nothing. The block, you can define that block as anything. There's no There's no guarantee that it is logically consistent in these. So there's no conceptual semantics within SysML. You can't identify the conflicting information easily. You can't infer that new information should exist based on existing information because you don't know what the existing information means. You're just allowing people to generate. Excuse me. You also can't check for the omission of information. So if you've got 5 engineers, and SysML models are designed to be used collaboratively, right? If you've got 5 engineers, one of them doing architecture, one doing design, one doing verification, one doing integration, one doing, let's say, behavior, and they're all inputting information into this integrated system model, you just have to trust that each of those systems engineers has the exact same mental model of what the system needs to be and do. And if they don't, they're going to input logically inconsistent information that has to be checked. And if it's not, checked and identified, removed or fixed, then you've got a logically consistent model that you're going to use to realize an integrated system. And those logical inconsistencies are going to propagate into your integrated system. You're going to get emergent behaviors. You're going to get verification and integration challenges. So the intended interdisciplinarity of SysML is subverted by construction. We are creating these really complex models with no guarantees that they are correct because they are not semantically connected. And I'm preaching to the choir here. All of y'all I've seen this in some form of another. And I would like to say, this is a 2-hour demo here or exposition. So if there's any questions at any point in time, just interrupt me. I'm not too concerned about time. We're probably going to get out a little early.
Actually, since you asked,
please.
Since you asked, Michael, so I really like how you kind of put like project management and project engineering, like on two sides of effectively some kind of a conceptual map. And it seems that the kind of problems you alluded to before could arise when there's some kind of a one-to-many relationship, like one concern that might arise in, say, in a project management team, but that concern actually maps to multiple elements that cross boundaries on the project engineering side. Or conversely, there might be one so for example, I don't know, risk of explosion that might straddle multiple elements, right? And conversely, there could be a project engineering or systems engineering concern like, I don't know, throughput, that in turn, it maps to multiple effectively teams that are responsible for components that are involved in the information path where throughput is assessed. And so when there's now miscommunication, miscoordination between all of those elements that on one side that need to somehow coordinate to address a single concern from the other, I could see that could basically result in inefficiencies, rework, addressing those concerns later because nobody is prepared to bring up these concerns in a coherent fashion.
Right.
Whereas things are simpler when effectively one team is responsible for something and there's another, I don't know, team or corresponding things on the engineering side, and the concerns basically don't cross boundaries. And so we end up like in this simplified world where everybody's cognizant of all of the concerns, requirements, and vulnerabilities of their systems, and we don't have to worry about other teams and other subsystems.
That's absolutely correct. The amount of information that is included here is incredibly complex. The relationships between all this information, the sheer amount, means that any solution that's going to address this is going to be complex. There's no simple answer to this. If there was, we would have found it already. But these information artifacts must be semantically related if we are to address some of these challenges, and communication of these challenges and inference of logically consistent information is going to be critical to the solution. So I do appreciate that. So when we're talking about these SysML models, and I'm harping on this a little bit just to illustrate the problem, but I do like SysML. There's whenever you're creating a SysML model, it's a blank slate. It is completely empty. Now there's profiles that can be downloaded for specific systems, but systems are highly varied. One profile does not fit all. So you've got to populate those models with this information, and then there's no guarantee of that information. SysML's not built to represent project management information. I know Sandy and Ryan Noguchi are trying to address this in the OSIM methodology, but currently you can't do it, and these platforms are incredibly expensive for enterprise scale use. I mean, they're very expensive, and so it's hard to motivate your enterprise leadership to pay for all this when they're not getting the expected, 30% increase or reductions of project time. So just to recap all this, and 1 and 4 drawback from the introduction section, we've got schedule slips leading to cost overruns, which are frequent, and that is a result of the system design being out of sync with the project plan. All the activities required to realize a given system design being out of sync with that. And all these aerospace enterprises, JPL and all the NASA centers included, they're relying on a lot of these digital engineering platforms, many of them SysML based, for those cost and schedule improvements. There's no guarantee that using these solutions, these tools, are going to prevent logical inconsistencies in the model, and then having to identifying those conflicts and resolving them is part of what results in, oh, we need more time and ergo more money. So these things are all kind of wrapped up together, especially in our current digital engineering environment. So let's look at a couple of research questions that can help us contextualize the problem. We need to identify a semantic framework that can handle the type of complex solution we're talking about. We need to semantically connect all of that PM and SE information, and then demonstrate that this is useful, that this is functional. And so I've left out here a lot of the kind of introductory material on the ontology context, talking about what are knowledge representation languages, what are implementation languages, the different architectures of ontologies, what language can be used, Protege and Rosetta, because you are all ontologists. I'm trying to tailor this to the crowd, but if there's anything that you feel has not been explained on that adequately, we will be talking about it more today. I'm happy to go back on this. But we've got a couple problems here, is that we all talk about how much we argue over different terms and how they are used. There is a camp of ontologists that say that if you do not have definitions for certain terms, that we can't have a conversation about them, and I vehemently disagree with that. But there's a lot of information contextualized for PM and SE. It is not small. It is not simple. So okay, if you had a semantic framework, how would you know if it was complete? How would you know if it was useful completely for a given problem here? So we're going to look at what it means for ontological completeness, and I hope that you can all take this back and use this in your own work. This comes from 2 sources, Issa et al. And Pepino, but they talk about, they had 7. I've only included 6 of them here. There's 6 types of completeness here: schema, property, population, currency, metadata, and labeling. And not all of these can be handled only within the ontology for reasons we're about to talk about. Some of them have to be handled in the software. For Empire, it's this integrated project model. There's a division of completeness assuredness for the ontology itself, and what the ontology is motivating to exist within these socio-technical systems. So schema completeness is the really hard one. This is the one that we talk about most as ontologists. When we're developing terms and saying, do we have the right terms, and do we have the terms related to each other correctly? This is schema completeness. How many of the terms exist that you need to exist for a given use case? And so you need to define your use case really explicitly. You need to say what are all the information that is associated with that, and we're going to talk about that here momentarily. But once you have that, you can theoretically say that you are complete. But some of these completeness assessments are subjective. There's few objective measures of this. So when you're talking about property completeness, this is something that would happen within the integrated project model rather than the ontology, because this is saying that everything that should exist does exist. If you say that a magnetometer is a sensor and every sensor has a physical interface, and then you you create a system element and you classify it as a magnetometer, you can infer that it's got to have a physical interface. I mean, Megan was just going through this in OML. This is a relatively simple property of ontologies, but what what we don't see in the socio-technical systems a lot is the inference of the missing information due to this property completeness. So this is the ontology checking to see what information artifacts exist and what information needs to be semantically inferred to make the model logically consistent, which is a really powerful thing. And we're going to talk about this a lot today. Population completeness is something that is really dependent on the modeler. This is not something that can be captured directly within the ontology or the integrated project model, because this is, okay, you've got a system, and have you modeled all of the system elements, all of the functions, all of the interfaces? And you may not want to. Some modelers choose that, okay, we're just going to leave it at this level of abstraction and call it a day because that's convenient for us. And that's fine. Every model has a purpose, or at least it should. All models are wrong. Some are useful. So as long as it's useful, great, but it may not have high degree of population completeness, and that it's really just up to the user. So this one we're not going to harp on as much. You're not going to see this embodied necessarily strictly in the ontology or in the integrated project model. For currency, this is really, really important, especially for engineering change requests and baselining architectures. So let's say that you have over on the left here a stowed configuration, and it's got a couple parameters. In SysML, you call them value properties, but you can say that certain system elements have a photovoltaic absorptivity of 0.89. This is a certain configuration that has been defined. It is in a certain software mode. It's in a certain observation state. Cool. And then over at time two, some other time later in the end of life, that photovoltaic absorptivity is decreased. It's in a different configuration. It's in a different mode. It's in a different state. So we need to be able to say that the ontological class might be state, but it can have different instantiations at different times. And it's not that state itself is different. We don't have to redefine state every time, but you have to be able to represent the variance of some of these information entities over time. And so that's got to be included and represented here. This is something that can be embodied in the ontology, kind of half in the ontology, half in the IPM. We make sure it's possible in the ontology, and then we actually represent it in Empire. So then you have metadata. This is really important as well for the engineering change requests. So here we're saying on the left here, some engineer has put in an engineering change request about the nacelle of an aircraft. It is baselined at A17, the 17th design baseline for this. And we say, okay, this is submitted at a certain time, and the approval, it has not been approved or denied yet. So the approval is null here. And then on the right, you have a different engineer who submitted an engineering change request, and this is for baseline A19. It's at a different time. It also hasn't been approved. And both of them are being evaluated for approval. Are we going to approve these engineering change requests? But the current baseline is that A19. So is ECR1 still relevant? You've got to have this information represented, and this is another one that we built the functionality to represent it in the ontology and then actually represent it in the integrated project model in the software. And then finally, you have labeling completeness, and this is really just a property of human versus machine readability. So we might have a requirement that is human readable, and you will see in Empire that we assert that certain requirement types exist, and every requirement of a given type has a specific syntax, and there are no requirements of that type that do not have that syntax. So certain syntactical fields, and I've got appendix slides on this if y'all want to dive into it. But everything that is not in these kind of lower level, I don't know if y'all can see my mouse here, but if you've got these kind of lower level syntax elements, here we are just populating fields within this syntax. GNC subsystem goes here, measure magnetic field strength goes here, spacecraft goes here, payload operations mode goes here. This can be exported as machine readable. If we export just this, we can populate it back into a requirement. So this is the difference between human and machine readability. And this is a function of most databases. Databases can export in JSON or unformatted JSON or formatted, markup language. So this is possible in a variety of ways. So when we're asking how would completeness be determined for ontology concerning aerospace, PM, and SE, you've got to figure out which completeness types are captured in the ontology, which would be figured out in the socio-technical systems integrated project model, and what are the criteria for assessing completeness with respect to how you're integrating the ontology within the software. And this is not strict. This is not just applicable to Empire. These are just completeness for semantically linked data. It's not even just ontologies per se. So hopefully you'll find that. Go ahead.
Quick question. So seeing a lot of information about I know metadata is a subset here, but for lack of a better word, the metadata of the ontology and the completeness of the ontology. I found that a lot of the breakdowns between PM and systems engineering and why things get pushed down, like there's breakdowns of processes in there as well. So is there anything that we're going to be looking at? It's like how to contextualize an ontology for a design within the process of it, talking about ECRs, right? Somebody makes an ECR, it gets approved. Well, now that has implications to the manufacturing life cycle. The ontology perhaps should be defined in such a way where a breakdown of that rule can be identified.
I think so. We're going to cover a lot of information today, but everybody's got their own ontologies, and so everybody likes to espouse their own. So I didn't put a whole lot of specific ontology terms. There are some in the next presentation that is just contextualizing how these ontology terms get developed and written. To kind of jump ahead, semantic reasoners do not reason on definitions. So we spend so much time as ontologists saying, okay, we need to classify this term, we need to give it a definition, and then we argue about this human readable definition. To get on BFO for a little bit, we say that the specifically dependent continuant exists in virtue of X because of its corresponding relationship with A. And computers can't read that. They don't understand that. They reason based on the relationships. So when we define ontological classes, which are represented as queries, which you'll see momentarily, all we say is, okay, an integrated system element exists. What else should be exist? Say for every integrated system, there exists an X that should be Y, and we'll see more specific examples of that. But the definition of a term is simply the concatenation of its relationships. So a term is what a term does. And so I didn't spend a whole lot of time putting in a whole bunch of terms to kind of rehash. Everybody's got their own definitions, and the ICME vocabularies are fantastic. So
what you're describing to me, it sounds like you're saying you're defining a term by a pattern of relationships that any instance of that term must have in order to be meaningfully defined.
That's correct.
And then if you have a term for which you have no pattern, then it's like, how do you distinguish that from an apple versus, I don't know, a box of cereal? You can't, right?
Right. There is the thought that some of the functionality that we're looking for of this PM and SE integration, a lot of that should be handled in the ontology, and we will see that today. But some of it should just be handled in the socio-technical system in the software. Not every term has to be ontologized. We're going to talk about this a little bit later, but there are some ontological theories that came from the 1600s to the 2000 ontological anti-realism, mereological eliminativism, and they all kind of boil down to we only classify terms if they are useful to a given purpose. So we're probably not going to have definitions for things like apple and cereal, and I know that was just an example. But if I'm going to ask to wait a little. I'm going to ask you to wait a little bit on this, and then bring this back up after I've gotten into the ontology content in the second presentation. Is that all right? I could not hear, but I'm gonna
Sorry,
press
I'm
on.
nodding my head.
Please.
Yes.
No, okay, great. Please keep asking questions, but I think I'll answer that a little bit better later on. So moving on, we're going to assume that the ontology is completely defined and we have represented all the completeness types in the ontology or the sociotechnical system. So now we're going to talk about what do we get? Okay, we have done all of this and we are assuming that semantically linking this PM and SE data is going to fix one of the causal problem of PM and SE disjunction being a causal root of schedule slips due to cost growth because the system model's out of sync with the project plan. So what do we get if we actually do this correctly? What happens? How do we assess that utility? So we're gonna it's gonna jump around a little bit, and then I'm gonna try and contextualize it at the end. So a modeling methodology is something that is really, really useful. And it's like a roadmap that defines what the people who are modeling are supposed to do in what order. And when you have well-trained systems engineers, people with PhDs have been doing this a long time, they know that in the system engineering process, you're supposed to start with defining your stakeholders, and then you stakeholder needs, and then you associate stakeholder needs with requirements, and the requirements goes into architecture definition, and then you talk about verification strategies, and you correlate those to design principles. And it's not a linear process, and it's not supposed to be, but that is the traditional methodology, and it's something that only systems engineers really know. It's not something that discipline engineers learn a whole lot. So if they have that modeling methodology and they don't need to be trained on it, that would be a powerful thing. And when you get done with the methodology, it helps you define what done looks like within your model. And importantly, when you're using SysML, just the ability to create a Gantt chart, or the ability to create some information, the ability to create a requirement specification, that is not prescribing a modeling methodology. Saying that, okay, you have a blank screen and you can input any information in any order, that's not a modeling methodology. This is telling you exactly what to put in what order. So that needs to be contextualized here. Then you have these semantic reasoners, and this is something that everybody here is intimately familiar with. We can perform semantic inference. We've got consistency checking, classification, and querying. And these are all simple examples. They don't completely contextualize what all these four functionalities can do. These are not even the only functionality of semantic reasoners, but we're going to talk specifically about inference here with respect to modeling methodology. So if you've got a launch vehicle that you're modeling using some ontology-enabled sociotechnical system, and some user defines an onboard computer as some integrated system element, if you know that every integrated system element must have a function or a capability, it has to do something, and that you know that you need to do that thing next if you're prompted to do that thing. And so the sociotechnical system infers using the ontology that you have to have that, and then tells the user to do that. So then the user defines a capability, which is just a function executed to some performance value for that system element. And okay, you've defined a capability. We know that every capability has to have a corresponding capability requirement. And we know that that requirement that has now existed must have a verification method. So now you don't prompt the people to create the requirement, you just do it. You just create the requirement. So you're modeling the architecture, modeling the design, modeling the functionality automatically relates to the requirements. And if you do that, you can do it both ways. You can either create the capability requirement, or you can create the capability requirement, which creates the capability. It is one-to-one matching the whole time so that your model is never out of sync with the requirement specification. And so then the ontology would prompt the user to select the verification method. And we're going to see this, an example in Empire shortly. So then the modeler selects that verification method for that requirement. And then we can infer, oh, well, this team is now verifying this by analysis, and it never had analysis before. So this team now needs to have analysis plan and analysis report as work products. So I hope that y'all could hear that using semantic inference, we can associate this with a modeling methodology and prompt users to know what to do next, to what information do we need to include in the model to make it logically consistent. And that is a really powerful thing, because
So when
there's
you
two
say
possibilities. Go
prompt
ahead.
users, you're saying prompt the designer of the ontology on the modeler. Or
Not
the
the
user.
designer of the ontology, the person who is modeling. So this might be a project manager or a systems engineer or a discipline engineer who is using the socio-technical system. And like Majid said earlier, when he was talking about Caesar and using OML, when they're using these platforms, the ontology is in the background. They never know that they're interacting with the ontology per se. They're just using the model. Then the model is magically telling them what to do next, and they don't really know how it's doing that, but they don't have to be trained. Think about this as something, if you're fresh out of college and you've only got a degree in mechanical engineering, you don't know everything about verification and validation. You don't know that every requirement has, one of analysis, inspection, demonstration, or test as verification methods, but this can help tell them what to do, even if they're really green. So there's two options here. And the word that we're using here is information artifacts. These are anything that could be populated into the model. This could be a work product. It could be a team or a team member. It could be an integrated system element. It could be a function. It could be a parameter or an interface. They're all information artifacts. So a user creates or selects some information artifact, and then the ontology could infer what information artifacts should exist based on that new information artifact and whatever related database fields it has. And if the ontology knows exactly what should exist, it can automatically populate that. This is like when you create that capability and it automatically determines that there should be a capability requirement with a specific syntax, and it automatically populates that into it. The other option is that the ontology infers that some other information artifact should exist based on whatever the user populated, but the ontology doesn't have enough information to populate it. So this is saying, okay, you've got a capability requirement and it needs a verification method, but the ontology cannot infer what that verification method should be, in some cases. In many cases. So the user still needs to select that we're going to verify this by test, or we're going to verify this by analysis. That's still up to the user, but we're going to prompt the user to do that instead of automatically populating on itself. So those are the two options here that result from when you're embedding semantic inference within these software tools. And now we're talking about speed. So this is where I told you I kind of jumped around, but all this is leading towards semantic inference, enabling a modeling methodology, which gives you speed of developing a logically consistent model. So there's kind of three things that might result from this. If the user is doing something and the ontology infers that logically consistent information should exist and then just goes ahead and does it, that's one less thing that the modeler has to do, right? They don't have to atomically define a bunch of logically consistent information. We can infer that it is. So there's less you have to do to create a fully useful model. The second one is that you don't have to check for logical consistency. If you're guaranteeing logical consistency under the hood, if we agree on the ontological rules and how those rules are implemented in these software tools, then you don't have to spend time checking to make sure that it's all logically consistent. You can just trust that it is. The third one can go either way. So it can either reduce the amount of time spent or increase it, because when you're inferring that things should exist that the user omitted either intentionally or unintentionally, if they were saying, oh, I should have included something but I didn't, I need to go ahead and include that. That is something that they would appreciate. Oh, I need that. But if they were inferring something that they hadn't planned on including just because it was out of scope of what they wanted to, then that would be more that they had to do. It increase their development time. So the first two would reduce the speed. The third one could either reduce it the first two would increase the speed of modeling, reduce the amount of work that had to be done, and the third one could go either way here. So within the scope
a
of
little bit into something that I asked earlier, and you said hold it for later, and I will just. It sounds like here with a properly designed ontology, we can be driving a process on how to properly create a model. You can also abstract this to just general processes, right? I come from the enterprise data management team, so not only looking at systems engineering data. So consistency within data, within other systems, within manufacturing systems, within supply chain systems, right? If they enter a certain information, if the ontology is set up in such a way to know that if you enter that information, this other thing should also be created, you can be driving a process.
Mm-hmm.
Okay.
Where the process driving is something that we are missing in our tools right now, and it is possible. We have the technology. We're good at this. We develop these ontologies. We know how to use semantic inference. The problem is that our socio-technical systems are not taking advantage of this, and there's a lot of nuances to this because where is the ontology stored? How is it built? How long does it take to infer? If you've got 1,000 people using an integrated project model, and each of them, whenever they create an integrated system element, it is going off to the ontology, and it takes 400 microseconds to run the calculation and return the example. That's not fast enough, because for everybody using that model, it's going to lag for like half a second. So this gets into what tools are available to us to build these ontologies, which is, I built ontologies for 3-4 years using Protege, and for reasons that I think we'll talk about a bit, it wasn't meeting the needs. We had to relate, project management systems engineering are highly complex. You're relating 4 or 5 or 6 things at a time, and then performing conditional logic on those in your semantic reasoners. And if you're relating that using binary predicate ontologies, well, you'll need to use reified relationships, or you need to create an exponentially increasing number of relationships just to reason if you've got 4 or 5 or 6 things. So how the ontology is built is incredibly important for the performance of these ontology-enabled software tools, and we only have a couple of tools available to us for building ontologies. Magid and their team has produced a really useful one, and Protege has been around since 2001, but we are limited by our tools in our ability to embed this into software. And so that's what we've kind of tried to circumvent in this present. I cannot assert that what we've done is the maximally useful way, or is the most complete, or is the perfect methodology. We have tried to create a way to circumvent the lack of tools available for a performant distributable ontology underpinning these software platforms. So that is, there's serious challenges here, but we have the technology. So for 2 models, one built with legacy methodologies and one built using these kind of ontology enabled methodologies, for models of the exact same fidelity and accuracy, which may not be apples to apples here, could it be developed faster using ontological inference? And if we're saving time in the development of these models, especially if we're creating models that align the project plan with the system definition, then we're going to save costs, because we pay people in person hours. So is that effort or person hours lessened? How could we compare it? How would we know if the effort was less, and who would verify that? So we'll talk a little bit about how we're planning to go about that. First, we have to build the ontology. Then we got to build the socio-technical system that can use the ontology. That is Empire. We got to integrate the ontology within the database to make sure that we're not getting that call and response asynchronous lag time for distributable models. And then we need to model a variety of different system or integrated project models for systems as case studies. And then I'm going to present those to some subject matter experts at the end of my PhD work, which should be done in about 12 to 18 months, and then characterize that utility. So within the ontology, we got to figure out, and this work has already been done, I just wanted to contextualize it for everybody. Do we want a reference ontology, or do we want an application? Do we want this to have layers in a top level ontology, or do we want it to be self-contained? The KRL here, I moved the KRL stuff to the appendix, so excuse me for not writing that out. The knowledge representation languages. How are we writing the terms and the assertions in the terms, and then how are we implementing those into code? So you're contextualizing the ontology in multiple languages, because I know Protege and perhaps Rosetta would disagree here, but I would say that perhaps the best languages for writing ontologies are not the best languages for implementing them in software, particularly database integrated software. So there's a division between the ontologist labor and the software development labor, and the ontologists usually don't understand high-level full-stack software development, and the full-stack software developers do not understand ontology. So there's a translation layer, which we'll see here in a bit. And finally, how are you planning to integrate the ontology into your software? You've got to have that scalable performance. And assuming that if you're going to have 50,000 work products or 50,000 people looking at this at a full scale, fully useful model for your Raytheons, or Northrop Grumman's, or Lockheed, you're really big, any NASA. I mean, you might have a lot of people looking at this and using this. You've got to have that ontology to be performant in it. With respect to these completeness types, I do not think that the best way to approach schema completeness is to read all of the systems engineering and project management textbooks and then to just contextualize all of the information therein. Instead, we're taking a practical approach here, where we're taking a life cycle, the NASA Single Project Program Robotic Mission Life Cycle, which we'll see in the examples, and saying what are all the work products that are required for that life cycle, and how those work products distributed across each of the stage gate reviews. And then each of those work products is a set of work activities that must be completed in order for the work product to be realized. For each of those work activities, there are a set of terms and relationships between those terms that would model the information in that work activity. And if you have all of your work products for all of your reviews within the life cycle, and all of your work activities for all those work products, and all of the terms and term relations for all the work activities, you have, in theory, captured all of the information required to execute a full project from both a project management and systems engineering perspective. So we're taking that practical approach, which is limited in utility to just, or not perhaps just to this life cycle. It is extensible in many cases. But as we build in more life cycles into this, it will get more and more useful, because we're not just looking at a specific aerospace system or a specific NASA life cycle. For currency, we're utilizing state dependence as a mechanism for that variation of parameters and configurations. The states coming from the parlance of Wasson. Wasson, I think, did a really good job at contextualizing the different types of states that exist for systems. And then we've got to build the socio-technical system. And this is Empire. This is a lot of work. It has already been done to a large extent. Empire is pre-alpha. It is not working. There are things in the demo that you're going to see that are not completely functional. There's things y'all are seeing the bleeding edge. We didn't leave out any of the stuff that doesn't look good. So it's still very, very much a work in progress, but it's got to be distributable. So we're building a web-based platform at the moment, but you've got to be able to represent, okay, I need this ontological term. I need to build UI content for it. It's got to work on Firefox as well as Chrome, as well as Safari. You got to have diagram-based development, because the textual and diagram development is really useful. You got to be able to rapidly instantiate models so that you're not working with just a blank slate. And then relational databases are not easy. There's I think 9 levels of database well-formedness. And then if this is going to be useful to these large aerospace systems, the government's got to be able to use it. So you got to host that information on the servers. And finally, who is getting access? Who are the people that are actually using this? That's really important too. So with respect to property, metadata, and labeling, this is all being handled within the socio-technical system, semantically inferring what information would make the model logically consistent, creating a metadata log so that we know exactly when information artifacts are populated. And then the labeling completeness is just, okay, I have a bunch of information in this model. Can I export this to a Python? Can I export this to JavaScript or TypeScript? If I want to take the data that I've rapidly inferred to exist, and I want to use it for other models that use different software languages, we need to be able to make that possible. And that's something that databases do pretty innately. That's not something I'm so worried about. So with respect to figuring out, okay, is this useful? There's not a lot of literature on how long it takes to build these models, who builds them for what purposes. A lot of this is very hush-hush, in some cases hidden behind classifications. And a lot of these, we talked about integrated system model information and project model information. A lot of these enterprises are using like 4 or 5 different software tools to contextualize all of this information. So if you're comparing what one model does within one software tool against the utility of 4 of them, it's not exactly apples to apples there. But you can develop performance measures to compare the utility of all of them. How fast are you doing it, the value. So we're taking a look at that. And to validate this, it would be better if we modeled, 10 different systems to get a whole lot of them. But that I've been in school for a long time. I'm ready to graduate. So we're gonna do one expert built system. Expert meaning that the system really well. I've been chief engineer for the satellite program. We got one that we've been looking at, and then a system that I don't know really well. And Kepler 16b is one that has been proposed. I think I want to talk to the folks at JPL a little bit more, see if we can get a system that has been developed, see how much data is available for it. But something that I just don't know all that much, that I'm not as familiar with. So the results of that validation will be limited, but it's at least a step in the right direction. And then we're going to develop a questionnaire, and because it's university, we'll get IRB approval, and then host a couple demonstrations where we show a lot of the stuff that we're showing today, but in a much more well-formed, fleshed out manner. Where we're saying we're instantiating these integrated project models. We're going to show the development process for developing IPMs using the semantic inference, the modeling methodology that we get. And then, okay, how do you use this information that is well-formed to actually make decisions about your model and system, or about your project and your system? Because it's not just about having the models. We use the models to make decisions. So ultimately, this whole effort is about facilitating good decision management. We are talking about not making it easy for people to succeed, but making it hard for them to fail, giving them not just the right information, but contextualize in a way where they know that it is consistent and they can trust the information, so that the kind of epistemic uncertainty, the variables that they're not sure about, are minimized as much as possible. So a couple of questionnaire topics here. We're going to talk about person hours and costs. We're going to talk about soliciting PM and SE information from including them, and then actually representing that information in there, the value of the semantic inference as that modeling methodology, the value of verification, integration information, how much you can trust the model that has been built, and then kind of exportability and the overall value. So we'll be getting a whole bunch of subject matter experts in a room, and if you'd like to be one for kind of this will happen right before we release all this open source, which, by the way, that's part of this. We're releasing all of this open source. We want the community engaged. We want this to be maximally useful. All the utility is not going to be behind a paywall. So we need to know how to make it maximally useful for the community here. Anyway. So if you would like to be one of the SMEs that we demo for, just please let me know, and I'll put you on a list and let you know whenever it's ready. So I expect to have published the ontology and the socio-technical system, describe the project management system engineering within a single integrated project model to demonstrate that the semantic inference works as a modeling methodology, and then what kind of cost reductions we're getting as opposed to using those legacy systems. Where for the ontology itself, this is an application ontology. It does not have top level or any kind of striations. Like, we don't use CCO or BFO or anything like that. Importantly, right now we don't even use inheritance. It's a flat ontology. It is, every term is flat on the same level. There's not really levels or inheritance between the terminology that's being developed. The knowledge representation language here, we write out the relationships, which you'll see in the next presentation, in first order logic, and then we translate those into English. The first order logic is to make sure that the math behind all this is consistent, that we can use mathematics to prove that we're not making that we're not we're not building logical inconsistencies into the relationships themselves. We translate those into English for the software engineers, who then translate all of the conditional logic into TypeScript. So not only did we have to build the ontology for it, we had to build our own version of a semantic reasoner for the database integrated aspect of this. What we'll get out of this is that rapid distributable inference of information within aerospace socio-technical systems, and those early engineers who don't know what they're doing, they can still build these useful models. You can still trust that they're not going to screw things up too bad, which will allow them to make more decisions with more confidence. Don't make it easy for them to succeed, make it hard for them to fail.
Does this mean that Empire has a OSDK, and by OSDK I mean a ontology software development kit?
We're working on it. That's I'll say it again later, but the Empire is incredibly complex, and the ontology part of it, the EOS, which I'm going to introduce in I think the next slide, is very complicated. So right now it is incredibly complicated to build the ontology and then translate it into the software. I haven't gotten to streamlining yet. That is a weakness in this approach at the moment. It's working, but it's not easy, which makes it difficult for community engagement to get started up. So that is a problem that I'll need to address, relatively soon. Here's just some of the aspects about the different completeness types. We left off population because that's modeler. That's dependent on the proficiency or desires of the modeler. And then finally, I am expecting this to provide drastic improvements of speed in the amount of time and effort it takes to create these useful models. When you can infer from a very small set of information all of the rest of the information, then you're able to rapidly build this out. And I do mean that if you have a set of requirements and you write those requirements in the controlled natural language syntaxes of Empire, and then put those requirements into, you just start with the requirements, that's all you do, it'll build out the rest of the information. You can build out the entire model just from having a requirement specification. You have to have it in the right syntax. So, we'll probably get on some LLM work of translating the kind of uncontrolled natural language requirement specifications that a lot of these enterprises use now into the controlled natural language syntaxes that can then be used to build out all of these big models. But I'm expecting the time and the effort and the money to be decreased dramatically, but it doesn't matter what I think. We have to have the subject matter experts comment on that using that questionnaire. So here's the acronyms. Empire is the engineering management platform for integration, realization, and execution. They're fancy words, but they mean something very specific in the context of Empire itself. And EOS is the Empire ontology system. Last year, I came in here talking. We had, we were calling ourselves the Unified Ontologies Foundry and the UOS, Unified Ontology Suite, and we've kind of done away with those acronyms in favor of just grouping all this into EOS. We've been doing this since 2023. It's only 2025 now, and it is myself leading kind of the conceptual development, and there's a guy named Carlos Damani that I need to make it very clear that none of this would happen without him. He is working effectively pro bono on all of this, and the vast majority of the software content that you're going to see is all Carlos. Carlos is fantastic, and I cannot give him enough praise in this work. But it's a very, very small team. We just brought on another guy named Dalton, who we're kind of teaching a lot of ontology principles, and he's handling a lot of the EOS coding. But he's not even out of undergrad yet. So we've got a bunch of young people that are just doing our best here. And we've created something kind of special, and it's very early days. This is all pre-alpha. So with this, let's get into the first demonstration, which shows what it means to instantiate models using an ontology-enabled system. This is the introduction of what Empire looks like, and it is how do we get people to start a little further on just by effectively, y'all have used TurboTax before, or the concept where it asks you a bunch of questions and then it fills out the information for you. If we can get people to fill out a couple of non-ontology data. When is your project starting? When is it ending? What life cycle are you using? And then we associate the life cycle is an ontology class, and the type of system that they're building is an ontology class. And when we use those classes, we can then infer what kind of information should be populated into the model just to start. Sort of like a profile in SysML, but a lot faster. So with that, let's jump into this first demo. So here, we're calling this the Empire Wizard, but it needs a better name. We are going to start building an astrophysics spacecraft. Just to start, we gave a demo to NASA Goddard, so we've kind of stuck with this. So here we're looking at a sector, and this sector is just supposed to guide people to certain ontological classes where, we included all this. We don't have ontology information for all of these, but aerospace we're working on. You pick your project start date, which, is just today. Your operation date just has to be at some point after the project start date. And then your project end date just has to be after the operation date. It can be a little bit after if the system's operating for a short amount of time, or if you have a system that has recurring missions, it can be a long time. We're contextualizing missions in here as well, but we're not really showing that today. So then all we're doing here is just guiding people to different ontological classes. So we're classifying spacecrafts. We're saying a space system, and they're selecting spacecraft here. And this is the first place where they are saying what ontological class they're using. But again, they don't know that. You're not supposed to show that to them. Then they're selecting what kind of life cycle. The classic V is if you don't know what what you want, you can use that one. And then we've included a couple life cycles here that are specific to NPR 7123.1D. But we're going to select the single project program robotic mission lifecycle. And these are all the reviews that exist within that lifecycle. So you've got mission concept review, system requirements review, mission definition review, PDR, CDR, all of that. And NASA contextualizes these in terms of risk posture, which we think is a useful thing. So between A and B, there's not a whole lot of difference. But when you get to C, you're starting to move faster. You're accepting more risk, and you're not going to check every nut and bolt, but you're going to move a little bit faster. It's still possible to select which reviews you want to have, but we're making suggestions here on what we think would be useful based on this this timeline. And some of the reviews are combined, and that they happen at the same time, which exists on NPR as well. We didn't just make that decision, but we're selecting these, and these are the ones that we're going to go with. So here we've selected the life cycle and we've selected the class, and we can infer a lot of information. What teams exist, what the baseline of the integrated system element, what does every spacecraft have? We also describe the enterprise, so we're describing what organizations and communities are around this. Work products for project management, systems engineering, and discipline engineering teams, just based on what kind of system they want to develop and how what life cycle they want to contextualize that within. So you submit this in, and so now it's checking AOS, and it comes back and says, okay, this is your model. You are not starting at a blank slate. We are beginning here. So now we are with the project management team. And here you can see the work products that exist and work activities that exist under them. I don't love the horizontal work activity view. We're still working on a lot of this, but okay, we got integrated master plan, operational concept, project budget, and this is not information. You're not supposed to just check these out and check them back in. This is all sets of information artifacts that we want to populate within to Empire. Over on the right in the review status, we've got MCR and SRR coming up at the end of this review. We've got this review cycle that we're in, and you can see the dates of those. And then we've got information about the work product. We've just instantiated this, so none of these work products have been started yet, but there's target completion dates for all these. This is the schedule network for all of these work products. So certain work products are dependent on other work products. And that red line represents the critical path, the path that is going to take the most time. We use a version of the PERT method, kind of a modified version here to express optimistic, most likely, and pessimistic times. And we populated them all with the same, duration here. Nothing too fancy there. But using this, we can see how likely it is that this team is going to finish. Based on this, it's going to take 22 days to finish this critical path. So, and there's 23 days for the review. So it's about a 96% chance that they're going to finish this work on time. And that's a powerful thing. This is where we're starting to associate that systems engineering information with the project management information within this critical path. So this is what people in the project management team would see. But if you're on the systems engineering team, you have a different set of work products. You have a different schedule network, different information that you're responsible for. So the schedule networks don't look pretty yet. We're still very much developing this. But here, this is expected to take 25 days, and there's 23 days. So there's a 0% chance that they're going to finish this work on time, which means we need to readjust the expectation of how long these are going to take, or we need to allocate more people to individual work products to make sure that they get finished faster along the critical path. But we get a lot of tools, a lot of ideas for how to do this. But this is simple project tracking. This is nothing really fancy here. But then on the thermal control side, these discipline engineering teams, they have, again, a different set of work products that they are responsible for. And so now we're looking at, this is a system, a socio-technical system that can be used by project managers, systems engineers, and discipline engineers. And we don't necessarily have to do version control throughout the entire set of information. So here, again, same information. This takes them about 96% chance that they get done on time. But it's also should be known that these are not immutable. Work products can be added or removed, which we'll see. So right now, we're just looking at the executive dashboard for Empire. But over here on the left, there's all of these different information views for stakeholders, architecture, design, operations, integration, reliability, requirements, development, qualification, acceptance, verification, all kinds of good stuff. And certain ones of these have more information. Verification by analysis, which we're working on with the Systems Engineering Research Center right now. Shout out to CERC. And for operations, you're defining the ConOps and operations concept. David Wagner and I have been looking at some of the goal-based operations work that JPL's done, and I think that would be a really useful thing to include in Empire. We're working on that. For project management, you've got work, schedule, earned value management, cycles, reviews. Acquisition is something that we're really looking into so that your vendors can even use these models and gain access to it. And if you say, okay, I need to buy something that does a certain thing, I lay out all the requirements for what I'm trying to buy, what are all the functions and interfaces that it's got to have, and then the vendors can come up with a solution that can sell it to us. So we'll have better contractual agreements between them. Whenever you select an information view, now you're going to select what kind of information or the system element you're looking at. Empire understands systems in terms of the integrated system, which is what you're designing, the enterprise system, which is the different organizations, what teams exist. If a team exists, team members get allocated to teams, and that kind of gives them permissions. We also have environments such as development, qualification, acceptance, operational, and transportation environments. And here you can see this is my login information. Everybody has their own login, and you can use your .gov or .edu emails because we use Clerk for the authentication manager service. But here we're just going to select thermal control as an integrated system element. And we select this, and then we're going to go to the architecture diagram, and boom, here's the architecture diagram. Go ahead.
Easy is it to extend the underlying ontology? Just coming from enterprise data management, I'm thinking about how we can use this not just in systems engineering or project management. Sorry, not, but across the entire aerospace business lifecycle. So we're talking about planning. You could do something similar for execution as well. So how easy is it to extend if we wanted to use this? And then a little bit more technical question here, using other authenticators like Okta? So two questions. One, how is it to extend, and then Okta? Yeah.
The answer to the first one is currently not easy, and that is the focus of the second presentation is actually how does this get developed? What can we actually do? And in the interest of time, I do want to move to that so that I'm not keeping y'all too late here. And the second one, we did look at Okta. Right now, we're using Clerk. Originally, we were using Amazon Cognito, but I don't think Okta would necessarily be a problem. That's more of a software development question than an ontology question. And I myself am not a software engineer. I have undergrad degrees in mechanical and aerospace and a master's in mechanical. I'm doing PhD aerospace systems, but I'm not a software engineer.
Right. That answers it. Thank you.
So I'm going to shift over to a second demo. Are there any more questions before we get going with the second one?
We're good. Go ahead.
All right. So moving on to the second deck here, we're going to talk about the structure, the function, and the process of what Empire and EOS are. And this will get a little technical, but this is the right crowd for it. We're going to introduce all the kind of concepts. We're going to look at the overview. We're going to talk about the development process of the ontology, which is what that question was just about. We're going to look at some detailed diagrams for how this works under the hood, and then we'll show a brief demonstration, and then we'll look at kind of where is all this going. And I hope that everyone will be able to see the power of where this could go if we can make it palatable for the community to engage with it. But there's a lot of work to do. I mean, this is pre-alpha. We are very early days. We're looking for feedback. I'm looking for perspective, but nothing we're doing here is perfect or right. We've got a long way to go. So Empire is a web-based framework that was developed specifically for ontological inclusion to help facilitate project management and systems engineering, particularly for complex systems. It's building the integrated project model, which includes the PM information and the SE information. And it's trying to facilitate that semantic inference to get that rapid development of model information, ensuring that it is logically consistent. We're aiming for open source release in 2026. It will not be good. It will not be useful when it first gets released. But if you're not embarrassed of your MVP, you've launched too late, right? So here's a couple of the software tools that we use. It's not all of them. We've got a journal paper coming out in Acta Astronautica, which covers a lot of this. But if you're familiar with software development, you're probably familiar with a lot of these tools. React is a really big one. That is the JavaScript framework that all this is built on, and Prisma is the database tool that we're using. So you'll see a little bit of that here. EOS, the Empire Ontology System, is a TypeScript library that facilitates ontological inference specifically for Empire. It does not work for anything else. I mean, it possibly could. We've never tried, but it's built for Empire. It is not intended to be necessarily extensible outside of Empire. It's just an application ontology, no TLO, no MLOs. There's no natural language definitions. A term is what a term does. A term is just the concatenation of all the relationships that it has. And then we write these terms using assertions translated from first order logic in English into TypeScript. And that's where the conjunction of the ontologists and the software engineers really come together. This is just a simple diagram for how Empire and EOS work, and I've kind of marked the TypeScript files with a fun little star. So down at the bottom, Empire is users are doing things in Empire. They're creating and selecting information artifacts, and then that is going into a flow. I'm sorry, I think somebody with a vacuum is going to come right up next to me. We're inputting this into this EOS flow script, which provides objects to the query class creation, which translate those objects into classes. And then those query classes are then going to result in conditional logic that get run for individual queries. And so it's important to note that we are not developing ontology classes for just like integrated system element. It is integrated system element is created query. We are writing it for the query. So if the integrated system element is created, what else should exist? This is where we're saying that Empire is complex and EOS is complicated. As far as we know, this has not really been attempted before, and it's very much a work in progress. So the folks in this room, we really want to hear back from you. This is not built using the traditional methods of, say, protege or binary predicate ontologies, because they just were not getting us the performance and the semantic inference, the computational logic, where you're inferring things about, the relationship of 3, 4, 5, 6 things at a time. So there's not RDF schemas here. But if we can make this palatable for the community, it might be really useful. And it's early days. I have no idea, but I'd like to think that this could be really useful, but everybody thinks that about their stuff. So there's just looking at the Empire and EOS as a whole, there's 8 atomic operations that can happen within Empire with respect to these information artifacts. A user can create some information artifact, or they can remove it. All the ones in the parentheses are just the opposites of these. You can select. So creation is, there's infinite things that can be created. You can create a team, you can create a team member, you can create an integrated system element or a function or a capability or a requirement. It's kind of unconstrained. When you're selecting for something, you're selecting from an enumerated list. So you have a list, 4 verification methods: analysis, inspection, demonstration, and test. If you select from those lists, then that becomes a little, it gets handled a little bit differently in the code. Prompting is not something a user does, it's something that happens to the user. So AOS is outputting prompts that then the user follows to do what they want to do. This is that modeling methodology that gets prescribed. And if certain things get removed or deselected, those prompts can be removed as well. And then finally, we want to make sure that INCOSE and the Project Management Institute are on board with this. So, or they at least, espouse the strategies that we're using. So execute and conclude are really just specific to processes. So INCOSE's System Engineering Handbook contextualizes a lot of processes, and by INCOSE's words, they're too dependent on processes. But you can associate work products being completed or certain acquisition processes that they don't happen within an entire review cycle. They're kind of self-contained. We want to be able to say work is being done where, okay, you can see what all processes are being executed at a specific time. And it's not really something that the user does. It's just kind of a check. So when people are using Empire, what does this look like? And you'll see a demo here shortly for not just instantiating a model. They're going to populate this information artifacts. They're going to create things, or they're going to select things, or the inverse, they'll remove things or deselect things. And then after they do that, what's happening under the hood, under the UI, is that the UI is related to a database. And so when they're creating or selecting something, it's making a change in the database. And the database, it looks like data tables, and we got an image for that shortly. But then those changes are provided by AOS via TypeScript classes as these objects. They're saying, okay, something's been created or selected. There's an object that get passed from Empire to AOS on that. So then using that object, the database changes are associated with ontological queries. And these are the queries that we're creating the different, the rules for, the assertions. If X exists, then Y and Z, but not, A, B, and D. If a user creates an integrated system element is created query. User selects a verification method analysis is selected query. We're only doing this if it is useful. If you're familiar with ontological anti-realism and mereological eliminativism, it kind of boils down to there is no one true ontology. Ontologies are just ways to slice what exists, what does and does not exist. So if you the only property of an ontology that matters is utility. So if you build an ontology that is useful and it does useful things, then it is good per se. But what exists is community driven. You saw that list of all the different sectors that exist, like automotive and healthcare and energy. We don't have any of that yet. So we're trying to build a platform that is useful to people to build in this content, build in these terms, so that we can slowly build out Empire as an open source way for people to make good decisions. But the schema completeness would be effectively a moving target based on what people want to use it for. So whenever the conditional logic is or whenever the queries are passed into AOS is going to run conditional logic on that. And there doesn't have to be an output from the conditional logic. We're not requiring that. In theory, why would you have it if there's no output? Fair point. But we are not asserting right now that we know everything about the conditional logic or about the relationship between them. So we're kind of leaving the door open. So we know terms exist or queries exist, but we haven't related them to many things yet. So the conditional logic is run and results get populated back into the Empire database. And we're going to see a lot of that in this presentation. But if of those 8 actions, the first 4, so create, remove, select, and deselect, if those get outputs, then they're recursively executed. So it's not just that you have one layer of the user does something, we say, oh, what else exists? It also runs, okay, something else exists. If that exists, what else exists? Oh, for that third layer, if that exists, what else exists? So it's not just running what the user has done, it's taking the implications of what the user has done and running those too. So that gives you the full picture of logical consistency, and it's reducing the amount of work that users need to do if these ontology queries are made in a modular, recursively executable way. So then
like a
those
full impact analysis of changes in the model.
Yes, and what that's going to enable us to do is that when we baseline certain information artifacts, meaning that no changes can be made to those information artifacts without approval from a manager, we will be able to infer, okay, if you make this change, what else would happen? Which is going to be a very powerful thing, but I have no information on that included today.
So, question?
Please.
So for example, like to kind of like simplify things, suppose that we have some notion of a power load, like something that needs power, like an instrument, and then you have some power sources like batteries. So I could imagine that if a user creates a power load, like say a camera, it needs power to take pictures. I could imagine that, okay, in Empire, you could have like some kind of a creation to say, well, therefore, it must be connected to a power source. Oh, I don't have a power source. Okay, boom, I'm going to put, say, I don't know, a battery. Okay,
You're nailing it.
Okay, wait a second. I'm creating a second camera. The first one might be, I don't know, wide angle field, the other one, narrow angle field. Oh, it needs power. Well, wait a minute. I have a power source. Am I going to use the same power source or am I going to use a different one? How do you deal with this kind of thing where effectively you can infer for consistency that you need some kind of a relationship, but it's not entirely clear if the relationship should be to a new element or to an existing one?
To me, that inures to population completeness. Whether you state that a given power source is shared among multiple sensors, that I don't think that's something that the ontology or the sociotechnical system could decide for you. But you'll see this momentarily, roles, qualities, and classes get applied to various information artifacts in various ways. That if we infer that or if we say that this has the quality electrical, well, then we know it's got to have a power source. And so we know it's got to have electrical power interface. So by attributing these qualities and these roles and these classes, we can then infer that things need to have certain information. So all we have to define is, okay, what happens when you give the quality of electrical? What things do all electrical system elements have? And then by just prescribing it the quality electrical, you then infer that it's got to have all these other things. Now, which power source you use, ontology won't tell you that, but it can. We're building out simple tools using these roles, quality, and classes using ontological inference to say what all has to exist to make it logically consistent, and that does come from physics-based modeling. We are building physics-based modeling into this as a function of that, especially with respect to conservation equations.
So, but there's going to be, I'd imagine, a delineation of like, this is where I model in the ontology versus what I model in Simulink, for example, right? Because the question is like, I have two cameras now. Do I have enough power to supply to both of them? It's a physics question rather than an ontology question.
Yes, specifically that is going into the work we're doing with the Systems Engineering Research Center on trade space analysis. Daniel Dunbar has developed a system of analysis that has a lot of really useful information in it. So we're trying to build that into Empire now, and we think that's going to be a really good stepping stone into the goal-based operational concept information that David Wagner and I were working on for the Complex Adaptive Systems Conference. But it sounds like you're getting the vision. You're nailing that part of associating ontological properties or roles, qualities, classes with certain information artifacts, and then inferring that it's got to have other things that we all agree on that every electrical component should have.
So, Michael, I just have a follow-up question to I guess Nick, but it's so if you have a relation between two concepts that has a cardinality of one or more, it at least has to be one or more. You could infer it at least has to have one, and therefore you could propose to create that object to at least satisfy the minimum cardinality. But if there is a range like more, how do you decide to do one or two or three or like objects?
We built those into the rules. The examples that come to mind is if you have an integrated system element that doesn't have any children, nothing underneath it, and you create one integrated system element underneath it, well, we know that if an integrated system element has one child, it's got to have a second one, because if an integrated system element only has one, then it is that composite part. So you've got to have two there. So that's if you got one, you got to have two. But if we know that if it's going back to what we were just discussing, if you say that a integrated system element has the quality electrical, we know it's got to have a min1 electrical power interface. But if you want to give it another one, that's kind of up to the modeler. We just know that it has to have at least one.
So for example, you could define a vehicle to have maybe 4 or more wheels, and the reasoner could look at that and say, okay, you defined a vehicle, I have to create 4 wheels to satisfy this constraint. But why not 5? Why not 6? Why not?
Up to the modeler there. I don't know that we could capture that in the. We could create, a class for sedan, and we know that every sedan has 4 wheels, and we can auto-populate that. But if you want to give a sedan a 5th wheel,
yeah. Okay. So the reasoner here is helping you create at least a minimally consistent model, but then you may elaborate on that.
Yeah, that's correct. I'm gonna push forward just in the interest of everybody's time. Okay, go ahead.
Yeah, so there could be minimum cardinality and maximum cardinality built into the ontology.
Yes, that's correct. Okay, so number 5 is talking about how it's recursive. It's not just checking the output of the user action. It's saying the user action motivates the existence of some things, and then it says, okay, if those things exist, what else exists? And if those things exist, what else exists? It is recursive. So using it, let's look at an example. If the user creates an integrated system element, I've tried to kind of stick into this. The populated information artifacts relate to these database tables. And this is what the database looks like under the hood. When you're defining system elements, you instantiate certain data tables for a given system element. And then when an object gets passed, okay, you've made this database change and you pass that object over, it's associated with a query. And then we have this conditional logic that gets executed in AO. So we've got architecture diagrams later for what this looks like. But just here's the brief snippet of the code, which you're not expected to be able to read from here. But this is what it looks like. You're translating the conditional logic. It's a bunch of if-then statements that are organized into these queries. And each query has its own conditional logic file. So if any create, remove, select, or queries or deselect queries result from whatever the user did, then queries for those are recursively executed. So you've created an integrated system element. We know that there has to be an architectural composition requirement that gets created. So that gets created. We have asserted that every architectural composition requirement is verified by inspection, because this requirement is just saying that it has a system element. That does not need to be verified by demonstration or test or analysis. So we just say it's always inspection. That was a choice that we've made. Some of you may disagree with that. But if you just say that, okay, this exists because this requirement exists, well, then because this exists, we know we have to have the work product inspection plan and inspection report. And because you have these two work products, you get the prompts to select the team members that are responsible for those and accountable for those in terms of a responsibility assignment matrix. So the user just created an integrated system element, but all of these things get populated or prompted because of that user action. And selecting responsible or accountable team members, this had nothing to do directly with the creation of an integrated system element. But when you get the cascade of logically consistent information, this is where you're really starting to get the crux, the connectivity between project management and systems engineering. So here's a little bit about those qualities, roles, and classes. These are just ways that we label or tag information artifacts. There's a variety. We have not contextualized, which information artifacts can get which ones yet, because we're kind of just figuring out what's useful at the moment. We're not bounding them that way. But when you attribute those qualities, roles, or classes to a given system element or information artifact, it it motivates the existence of more information. It is itself a query. You say a query or quality electrical is selected query, or quality hardware is selected query. So that there's not really a limit to which ones you can apply, but some of them are mutually exclusive. You can't say something is no. I'm going to leave that off. That's probably more confusing. So with qualities, this is usually describing permanent properties of an information artifact. This is things like hardware, software, and electrical. So if you give it the hardware or the quality hardware, it's going to own the parameter mass. Every hardware system has that parameter mass. You do not have to, also give it that parameter mass. You just give it, you say what qualities that system element has when you're architecting the system. With roles, this is supposed to characterize agency. It's something that it may not, the person may not always be. It's just some role that it could fill. I got a question about, okay, what if you had a parabolic antenna that could sometimes be used as a sun shield, where that would be a role. It's not something that you're designing it to be, but it's something that it could be. For a team member, if you can say that a team member is the manager of a team, that's a role that they would fill that would give them more permissions of the software. When you're doing acquisition contracts, you can define acquisition contract managers. If you have a parameter, you can give it the role of a key performance parameter. These are just ways that we can attribute logically consistent information to different information artifacts within Empire. And classes work similarly, but this is where you're really saying
on roles, because we're touching it here. Roles-based access control, right? Some information. I'm assuming some modeler can have access to the design of some things. There are some things that are a lot more controlled. How does Empire handle that?
That happens, yes. So the permissions that are done on the authentication manager, the permissions that are given to the people are associated with these roles. The team managers have access to information about the performance of certain team members, because you give them, you allocate work activities to those team members, and are they completing them, on time? Those are, performance parameters that you don't want everybody to be able to see, but you'd want the team manager to be able to see. In general, we're trying to make as much of the model as possible visible to everybody, but not editable by everybody. So you can only edit the things that are allocated to your team. Thermal control couldn't edit something that flight software was responsible for. But we want to make thermal control able to see what flight software's got going on. Does that make sense?
Yes, thank you.
Thank you. So classes, this is where we're able to get a huge number of things. So if we say that it's a spacecraft, we know that every spacecraft has certain system elements. We've got certain teams that are allocated for those spacecraft. So just by saying that the system element is classified this, you can motivate the existence of certain teams with their own executive dashboards. Saying that a system element is a thermometer, or saying that it is a payload, that kind of thing. So if you give it the class thermometer, it owns a parameter measured temperature, and it has to depend on at least one interface within a system environment element, because you're measuring that. So you can infer those kind of things. And again, we in Empire, we had the ability to architect the environments just as well as architecting the integrated and the enabling systems. So we know that you have to have an interface, and that interface has to be with the system environment element. So getting into the ontology development process, which is kind of the what a lot of the questions have been about. First, we figure out what would be useful to represent an empire, and that's usually relating to PM, SE, or V&V. Discipline engineers are, everything that they're doing is some type of verification or validation. I mean, pretty much always. But users using Empire will always create or select new information artifacts, or the opposite, they could remove or deselect information artifacts. So we're figuring out what would be useful to include. And then we say, okay, is that thing created or is it selected? And then you define the query associated with that. So we want to be able to create a system capability. System capability is created query. We want to select the quality electrical is selected query. We define what the queries would look like. We define what the objects would look like to get passed into AOS in order to motivate the existence of that query. This is the really hard part. So 3, we're going to ontologize the hell out of this thing. We are going to say, what are the relational rules that exist? For every X, there is a Y. Every A can be related to B via C. and that we write these rules first using math, which the math is mainly for my PhD dissertation. It's not strictly necessary, but it is useful. But we translate those into English, and this is the part that's handled by the ontologists. We do not have a development platform for this. I would love one, but we only have so many hours in a day, and we're trying to focus on getting Empire up and running first. But we will need that ontology part, the development portal, and then we translate that into software translation. The ontologists generally do not understand full stack software development, database management, and then UI development. You've actually got to build what it looks like in Empire. And the full stack developers do not understand how to build ontologies, and the assertions for them, and to write them correctly with a well-formedness.
Is that the hard part, the translation?
Yeah. This is an enormously hard part. I've got a bunch of teams of undergrads at Auburn University who I've been training to do this, but they're all senior design students. They leave every semester. So I've got 2 more semesters where I'll be able to guide them into building a bunch of ontology classes. But it's not easy. But I've taught it to undergrads, so it's not like people can't do this.
Thoughts on using like AI code gen? Because new AI is very much like brand new grad, fresh out of college. You can get it. Yeah.
I think it would be a really good idea, at least as getting a starting point. If you can tell the AI how you want the rules to be written, and then say, give me a bunch of rules for these classes, it could get you a lot farther than just starting with a blank page. But I think the final version is going to be agreed upon by more than just one person before it actually gets built into Empire. So then we write those as TypeScript classes, and we use TypeScript because that's what the database uses, because we want this to be database integrated. We don't want a call and response when it's running the ontological query. We want it to be database integrated so that it is rapid, it's immediate. You performing the semantic inference without having to wait on anything, which makes this distributably performant. So you get a query file relating to that creation or selection of the information artifact. You were hooking it to the database, and this is really where the software engineers shine. And number 5 as well is where you're actually building the UI part for Empire. A lot of this right now is just directed by me. I tell the software engineers what would look good and how to do it, and then we go through a couple of weeks of, this looks good, let's change this. And then they build it, we hook it up to the database, we hook it up to the ontology, and things break there. We had one thing in the demo that you'll see as soon as I can get to it, that didn't work. It broke. So it's not easy. But then we test it after we built all the full functionality. Is this thing doing what we want it to do? So actually testing it by using the software itself. So as an example of that process, we say we want the ability to create integrated system elements in Empire. We think that this would be a useful thing. This is architecting the system. And we're talking about direct composition, same as SysML, because again, we want to export to SysML. So we don't want it to be too dissimilar here. So we're going to relate that query. We say the user is going to create that integrated system element. Integrated system element is created query. And this is where we start writing the rules. So, okay, an integrated system element exists. For every integrated system element, there exists at least one interface such that the integrated system element is dependent on the interface. For every integrated system, there exists at least one system function such that the system function is associated with the integrated system element. So you're defining, if you create the integrated system element, what else would exist? And these rules can get long. They can get kind of difficult to read. Every integrated system element can be realized as the output of an acquisition process or a development process, saying, okay, am I going to build this or am I going to buy it? And these processes are what, you select those processes, and that tells you, okay, you've got a couple work products associated with acquisition. Every integrated system element that does not have another integrated system element as a composite part has a quality foundational. That's a separate quality that is probably going to be a red herring today. It helps us do a little bit of determination on the typing of functions. But you can see that writing these rules is not easy. It's not simple. It is a math-based format, and even when the software engineers look at this, they don't understand how to translate it into conditional logic. So this is where the real breaks occur, and this is the part that has taken the most time. And I'd love to hear feedback on how this might work. If y'all want to email me, Majid has my email, and Joe Gregory in there has it as well. So if y'all will get my email from them, I'd be happy to talk more. But then they translate those rules into the TypeScript classes. This left one is what calls the that given class here, and the right one is the actual conditional logic itself. So, okay, we have written it. We create specialized page content. Okay, this is an architecture diagram. We are building the ability to architect it. And then we build the ability to actually create that integrated system element. We hook it into the database. Then we show the prompt structure, which you'll see in the demo that I'm hustling to. So these result in what we call cascades. So when we create that integrated system element, it's going to create an architectural composition requirement, because requirements are just contracts. Requirement specifications, they're just contracts. Whether you're communicating to your lower level discipline engineers what your organization needs to do, or you are a prime contractor contracting out to a subprime and you've got a contract for what the system needs to be and do, it's just supposed to be contractual obligations. And there's no reason that we are doing the requirements and the architecture and the design and all that separately. They should be built together. It should happen one-to-one. That way you don't have to define all the requirements and then translate that into the model. No, we're smarter than that. We can build the model and then just infer what the requirements are, as long as everybody agrees on the syntax of a well-formed requirement. So that separate query, architectural composition requirement is created query, would run because the integrated system element motivates the existence of that architectural composition requirement, and then you run the query for that architectural composition requirement. So this is that cascade of queries, and this is what it looks like. You've got that user action at the top, and I build these diagrams for the undergrads to understand how to translate the rules that have been developed into the actual conditional logic, the code. So these cascade diagrams are kind of like an intermediary between those ontological query definitions and the software that gets built itself. But you can see there's multiple layers of this, and they can get, depending on the conditional logic, depending on the fields in the database, they can get larger. So this is the exact same user creates an integrated system element, but the team did not already have an inspection plan or inspection report as opposed to the previous one. So we're now creating the inspection plan and the inspection report for these. So they can get pretty long. When these cascades execute, it's only the creation, removal, selection, or deselection that motivates it. And then there are prompts that get output for the creation, removal, selection, or deselection of other information artifacts. So these are kind of the three things that it does. It either actually create, remove, select, or deselect things. It can prompt the user to create, remove, select, or deselect things, or it can execute processes and conclude processes, which is really just for INCOSE and PMI consistency here. The modularity of this means that query, architectural composition requirement, is created query that can be run if the user creates an architectural composition requirement, or if the user creates an integrated system element and then AOS creates the architectural composition requirement. So it's modular in that it can be executed as part of a cascade, or it can be executed at the beginning of a cascade from the users. There's a couple nuances. Sometimes when AOS is checking like mid cascade, it hits a query where it looks at the database and tries to find some data table information, and the field is null. That means that it cannot perform the conditional logic. It doesn't have information. So it kind of snips that conditional logic off and then associates it with a prompt. And then when the user executes the prompt, it executes that conditional logic. Pending logic is a more complicated thing that we're not talking about too much today. And then finally, there are some cases where Empire can motivate the existence of multiple. They can create multiple or select multiple entities at the same time. And so you have to order those, which cascades get run in what order. And usually it doesn't matter. So let's look a little bit more under the hood. What happens when AOS is running? So why do we need this? Because some of these cascades get really, really big. This one specifically has to do with F prime out of JPL, your software platform. One of the things Empire can do is model software using F prime and then generate functional software using the F prime platform. We're not getting into that today, but we're building the ontology part of that so that you can actually just say you're selecting that and integrate system element is an F prime software project, and then it just generates everything that you need from it iteratively using this, and it is version control. Like all of these relate to F prime version 3.5. But you can see that these cascades have a bunch of different layers. You know, for this given user action, there's layer 1, there's layer 2, layer 3, layer 4, and layer 5. You need to be able to go down in terms of depth, and you need to be able to go side to side in terms of breadth. So the order in which these queries get executed, we need to make sure that all of them are being executed in what order to make sure that all of this happens correctly. So there's a couple
Given that
concepts.
you're using JavaScript, I mean, concurrent running of queries, not a thing that's currently supported by Empire? Like if they're not necessarily dependent on each other, you can run them at the same time?
We don't currently have a method to determine if queries are dependent on each other, but it's a good idea that I definitely think is worth looking into. But you know, if you've got something down here, this can only be run after this has been run. So it's not like you can jump down here and then like run this one before you run some of these.
You would need the knowledge of the lineage of the queries ahead of time before you start executing them. But there's a couple of methods that you can use. Yeah.
Yes. And I'm all ears. If y'all have got ideas, really cool technologies we can use, hit me up. But this is what we got so far. So these placeholder logs, this is when we know that queries need to be run. Like we're recursively executing all of these queries. They get added to the placeholder log for, okay, we're going to run these at some point. This is how we are determining what needs to be run within a given cascade. And then you have these order and priority indices. Priority index I determines what layer you're going down. So that's kind of your depth. And order index K determines that breadth, the horizontal location within the layer. We have this has run flag, which says, okay, a placeholder, a query that's in the placeholder query log has already been executed. And then we have the cardinality, which is the number of queries within a given layer, within a given priority. So if I go up here on this one, the cardinality would be 4. And we can determine that because, this output 4 things, 4 queries need to get run. I know that the cardinality is 4. So when we compare the cardinality to the order index, that's how we know we've hit the end of a given layer. So has run flag and cardinality. Again, this is that structure. So Empire is inputting, you get some user action data that goes in this AOS flow TypeScript file, which goes to the query class creation, which runs this conditional logic file, which has files for every single individual query, which is checking the database as needed. And saying, okay, I need to know this information to run given conditional logic. And because it's integrated with the database, there's not a performance hit on that. So that's a really powerful thing. So we're creating classes for each of these queries, and then we implement those classes to store specific attributes for each of the database creations. And then we extend that query class that has the basic attributes to keep track of the order, priority, and the cardinality, which you'll see in a diagrammatic form. There's a lot of information on this slide, but this is just an overview of how the AOS flow file works. We get the Empire, the object provided from Empire. AOS converts that object into a query class. The conditional logic is called for the query class. The output from that conditional logic goes in the placeholder log. We figure out the priority, order, and cardinality for each of those placeholder log queries. There is an output history log, which you'll see at the end. And imagine, I know we're getting low on time. I'm hustling, I promise. And then finally, we recursively run that until the process ends. I'm going to go a little faster. Prism is just a relational database. There's a lot of good things about it, but it's working really well for us so far. So this is not for reading. This is the overall flow that I'm going to very quickly step through. All right, we're going to start up here. So the user creating or selecting some information artifact, and then Empire provides that object into AOS. Aos converts it into a TypeScript class, same as what we were just looking at. It runs the conditional logic on that user-initiated class. I would say, okay, does Aos have everything it needs to run the conditional logic? No, it's going to check the database, and then it gets the Aos populates placeholder log. I did not include the information here about pending logic, where it checks the database and the database table that's looking for is null. I just didn't include that here. So then the database is going to represent that user-defined information artifact, and then Empire is going to create or remove or select or deselect, prompt, deprompt, execute, or conclude any of the information artifacts resulting from whatever the user has done. So now we're getting into the kind of the cascading results. What happens then? So are there any more prompts or any more create, remove, select, deselect, or any of those that are in the placeholder log? If there are, we're going to initialize that priority index to 1. We're going to initialize the order index to 1. This is just a short example of what the code looks like. Just to say there's code underneath all of this. So going over here, we are going to select that placeholder value, that query that has a null value. We usually do this on alphabetical ordering because we haven't come across a case where it matters the order at which the results are populated in. So we're kind of just using alphabetical right now because we haven't hit a problem with that. We're going to assign that with the priority index I and the order index K. And then we say, okay, are there any more queries in the placeholder log with null values? Anyone that need the I and the K? If it does, we increment the order index and then we do it all again. So priority index is staying the same. We're at that same layer, but the order index is increasing for all of the individual ones in the layer. So once we've given all of them their indices, we set the cardinality for the highest one. So C is equal to K because K would be the highest cardinality within that layer. We reset the order index, and then we assign that cardinality to all of the queries in that layer for the placeholder log. And we say, are there any more that don't have the same cardinality? No, we continue on. So now we're going down to this middle section, coming in from the left, we reset the order index to 1, and then we run the conditional logic on that placeholder query. And it's the same as up above. Do we need to check the database? Yes. Do we have all the information we need? No. We go over here, and then that is added to the batch log that is going to be then used to populate the database with what's happening. We set the has run flag to true because we just run it. So same one up here. Aos populates that with the alphabetized query output. And then we pass that to the database. That database represents the changes, and then the changes are represented in Empire. So now you're getting the ontology results populated into the software UI. So on the way down here, we're saying, are there any queries in the placeholder log with null values? So this is saying, were there any new outputs? If there were new things added for that create, select, prompt, deprompt, any queries, then they're going to have null values. If they do have null values, then we're going to increment the priority level because we're going down a new layer. So we may not have finished all the horizontal parts of that, but we're going down a new layer. So every time we need a new one, we just go down the layer. So we reset order index K to 1 here, and we're going to come back up, and we're approaching from the left. So then we're just doing all this again. We're going to give all the ones that had null values their priority and order indices. We're going to set the cardinality for that layer, and then we're going to go through until they all have the cardinalities, and we're going to come back to that middle section, but we're going to pop back down here, assuming we've already run all the conditional logic, and then say, are there any with null values? Let's say no. There aren't any with null values. So for a given priority level, for a given layer, there's no more that we have to run. And so then we say, is the order index K less than the cardinality for that priority I order K stakeholder query? This is saying, are there more to run within a given layer? We don't have any new ones. We don't need to go down another layer. We don't need to increment the priority, but there might be some in the current layer that we haven't hit yet. So we say yes. So we're coming up here. We're only going to look at this one real quick. We're going to increment the order here, and then we're going to rerun this. So we're just finishing everything on that given layer. And if that produces more, then we'll go back up. We'll increment the priority. But if not, we do all this. We get the outputs, the results, set the has run flag to true. We populate the Empire database with the results of it. So then coming back down here, so are there any queries, the placeholder values with null values? No, nothing new has been produced. Is the current order is the current order index K less than the cardinality? No, that would mean they're equal. So we have hit all of the ones in that given layer. So the breadth of a given layer is handled. So no, we haven't. If we come up here, we decrement the priority. And if the priority index is 0, we're done. We're finished. We provide the full history of that cascade and we finish. Well, Zuck. Everybody loves a good Zuck in satire. So that happens if we're done, if there's no more to do, the priority index is 0. If that's not the case, if we decrement the priority and the priority index is not 0, and then we check, are there any that has run flag of false? So is there anything, we've decremented the priority, we've gone up in the layers. So is there anything on that layer that still needs to be run? If the answer is yes, so then we find the one with the minimum order K value that has run flag of false, and we just come back down. We run the conditional logic for it. We populate it down into Empire. Coming back up to the end, just looking at the right part of this, if the user does something and there's no outputs based on what it does, then we're going to say no, there's no more, and then we come down here, and then we're done. We're finished. So nice job, team. So I know that was a lot. Are there any kind of questions about how we're handling the logic on the back end? I went through that very, very quickly.
So Michael, I have a related question.
Please.
This algorithm you explained is trying to find to create a model to complete the model from a given state to satisfy a set of constraints expressed in the vocabulary. Is that correct?
The algorithm is designed to help us handle things like this. It's designed to make sure that we are able to address all of these queries in a reliable manner and to populate the results of those queries into the Empire database and subsequently the UI as the information is produced.
Okay, and by queries here, are they like constraints?
No, the queries are, we're saying integrated system element is created, architectural composition requirement is created, function is created, query is created, hardware or quality electrical is selected, quality hardware is selected, verification method, demonstration is selected, and those queries could be anything. And so then we associate the rules with those queries, and then the rules are translated in conditional logic, and the conditional logic is run for each one of these green items.
So the starting point to
is a user action.
This is the user will be or the I guess the methodologist here will be writing these queries first. Is that the first artifact they write?
Yeah, so the ontologist, we write, we say, okay, this content exists. We need to say, if this exists, what else exists? We're not defining a definition. We're just saying, what do we know is it always related to?
Which is like a cardinality of a relationship between things.
Yeah. If the cardinality is 1 or more, and you say, we know if this thing exists, we are sure that conceptually, we know based on physics principles or modeling principles or heuristics, whatever, we're agreeing that if this exists, then something else should also exist. And we can logic through those reasons. So we're going to include that on these rules and then represent it in conditional logic to be populated into the model.
Okay. So if you have if you can represent this information in logic, as you described, then to actually find the solution, to actually create the object so that these logic formulas are satisfied, is that an algorithm you defined, or is that like out of the box algorithm that can do that?
No, we defined it. All of this stuff is fresh out the bakery.
Okay.
I cannot guarantee it is right.
I see.
It is working. But it is certainly not the most optimal solution. We are exploring
Okay.
the way to embed real, true ontological utility into software for good things, but it's hard, and we are making mistakes.
I wonder if you've looked at a class of solvers called model finders, where you can give them a set of logical constraints. Like, for example, what was the name of that solver, Nicholas?
There's Alloy.
Alloy, for example, is the name of such solver. It's a SAT solver, SAT. And if you described your constraints with the SAT solver like that, then it will give you a candidate architecture or like a set of objects that satisfy your constraints. And if you click the button again, it will give you another candidate that satisfy your constraints. And so you could just focus on describing the constraints, and it will find these architectures that satisfy all your relationship constraints, but it doesn't have to be the minimal one. It could be anywhere in between minimal and maximal, so they are good at discovering architectures.
Yeah, I mean, in principle, yes. What Michael described could be cast as a model funding problem. In practical terms, though, Daniel Jackson, who defined Alloy, in his book about software abstractions, the very first sentence, one of the things he said, abstraction is hard. But one of the things that he says is that Alloy is really tailored for the small model hypothesis, or essentially the small universe hypothesis, in that it would work well if, say, Empire were limited to, say, no more than 100 things. But in practice, if you want to build, like, I don't know, like a real spacecraft where you might have 10,000 things, then model finders are not going to work. They're going to blow up, right?
I do think that we have created a structure. We have created an ontological structure that is embodied within the software. And I do think that neural networks in particular, if we say, okay, you're playing by these rules, you've got a spacecraft, architect the spacecraft for a given purpose and assign it the functions, assign it the capabilities, assign it the parameters, which y'all are about to see on the next slide. And I think they would be very, very good at that. That is emergent stuff that once we get the foundations right, we will slowly be able to build towards.
But there's a flip side in that what Megan was describing, where instead of using a model finder as a way to construct the model, with the model finding as opposed to the logical rules that you described, you could perhaps look at these kind of techniques as a way of verifying that, in fact, the encoding of the rules is in some ways correct. If you were to say, I described the logical constraints that Megan was alluding to, saying, these queries, there's a logical formula, in there, and say, write those logical formulas, let's say, in Alloy or something, and you were to somehow export a subset of your database in a form that Alloy can reason about, then you could actually ask it, is this still consistent with the constraints that you have? So that kind of verification could actually scale, because you're not then asking the model finder to elaborate a model. You're just now trying to check that a particular model is consistent with the logical rules that you've defined.
I would love to talk to you more about that. So I'll follow up with you via email. If you could point me to some of the relevant information there, because I'm pretty ignorant about this.
Let's get together. I will show you how it works, and then we can discuss more.
Please. All right. So now we're going to get into go ahead.
If you abstract this into solely like a graph problem, since you already know the definition of the ontology and you're trying to do impact analysis, there are some really good pathfinding algos that you can do to determine the lineage of the queries that you have to make So you don't have to do it recursively, right? So you can, I know ahead of time what the full impact is. I know those queries. I don't have to iterate. It's a lot more compute optimal than iteration.
Y'all are warming my heart because this is exactly why we're releasing it open source. This community knows nobody knows everything. Everybody has their own strengths, and it makes me really happy that y'all are seeing this and then immediately identifying what we could have done better, and what tools exist that might work better, because I certainly don't know all of them.
So Michael, there is a question, another question from Robert.
Go for it.
Roberto. So Robert, go ahead. You can speak it up. Yeah.
Yes, thank you. Can you hear me?
Yes.
Thank you. I have two questions, and apologies if I stumble over my words. I've gotten a couple hours sleep, and with the time zone difference over the last couple of days to listen to the presentation, so bear with me. The first question is, earlier you mentioned that you're trying to find a way to incorporate or to embed true ontological knowledge, if I remember the words right. Could you expand on that a bit? That's the first question. I'll get to the second after.
I would say that true ontological knowledge is a bit of an oxymoron in that no ontology is objectively more true than any other. We're trying to, just like any communal ontology, assert that you can do a certain thing in Empire. You can create or select some information artifact, and when that thing exists, what else should exist? And if the community can agree on that, if certain things are contested, they get left off. We just find the ones that everybody agrees on and then build those into conditional logic. Now we've got something that slowly becomes more useful, because it's not just creating the ontology for it and then using the ontology for a given purpose. You're using the UI of Empire to actually model your project and system, and you get the ontological utility out of it.
And could you say a bit more about what form the ontological knowledge takes? Is it just the logical formalization, or is it something else? What do you mean by it?
So we identify what terms need to be built. We associate those with a query, and then we create the rules for them. So those rules get written first in first order logic and then in English. And there's a problem where what the ontologists know what they want to say, and the software engineers need to translate that to conditional logic. So we use these cascade diagrams that you've been seeing as kind of a visual reference, as a trend, as kind of an intermediary between the ontologists, controlled natural language, mathematical English, and the software TypeScript conditional logic. So there's this translation layer of ontologists define the relationships using math and first order logic and mathematical English, and then we build these diagrams, and then we use those diagrams to translate the conditional logic. And then as long as we've got the UI content in Empire for actually creating or selecting that, we've hooked everything up to the database. You will see momentarily what it looks like for the ontology to actually be interacting with the users.
Okay, that brings me to the second question, which I'll briefly state. You mentioned earlier that you have some undergrads doing the translation layers, so the ontologist translation into symbolic logic, and then into the word escapes me at the moment. Pardon me. Anyway, so that layer itself, if I understand correctly, that translation to symbolic logic, that's pen to paper. Is that right?
The translation is the rules are already codified on. I mean, you could write them in a Word document. Right now, we have a GitHub repo where we assert all of these rules. And then I work with the undergrads who are software engineers in their capstone senior design projects, to model the diagrams, just to make sure that they understand what it is that I'm asking them to do. And then once we've agreed on the cascade diagrams, what they should look like for a given term, they translate that into TypeScript. They then write the conditional logic that gets used in AOS. And then we hook all that up to the database, which is not something that the undergrads can do. That's something Carlos does.
Follow up on that.
Oh,
Sorry, go ahead.
sorry.
Okay, so if I understand correctly, I'm not sure I do, but if I understand the undergrads who are doing the ontologist translations, if that's into, for instance, first order logic, and you had asked if anyone has suggestions on how to better communicate or teach them how to do that. This is something I think I might be able to help with in my presentation earlier. That if I understand your approach, it might be similar to mine, where I translate conceptualizations into first order logic. And my background from my past studies as an ontologist, part of that goes into how to teach these sort of symbolic translations. So if you'd be interested in touching base or perhaps bringing someone on from the outside to do the work, I'd be interested.
Yeah, I am not a mathematician by training. So the best way to write these first order logic rules and then translate those to English and then to the diagrams, and then to the TypeScript, I could definitely use help. So I'm going to show this demo just as it's the last thing that we show today. But I mean, Nicholas and Robert, yeah, let's get in touch. There's a lot of stuff that I could learn from y'all. So let's get to this last demo. So this is a model that is pre-existing. This is one that has been built out. We did not just instantiate this. We are in the middle of a project per se. So right now we're looking at the thermal control team's executive dashboard. And you've got all of we're in the preliminary design review PDR cycle. So they've got a whole lot of work products. I mean, it's almost all of the work products show up in PDR. It's a huge number. And I'll go ahead and say, we're over on the review cycle. We've got 39 days until PDR. We've defined when the preliminary design review is using that life cycle, which is editable, but we make the suggestions at the beginning. We've got information about the work product details, and now we've got information about technical parameters. So there's constrained parameters that are not associated with functions. We're saying, okay, it's, cycle target, we're trying to get this under 3.5 kilograms. And then our final technical measure, we're looking for under 3 kilograms. And then for performance values, we've got this operational heat generation, where we defined some cycle targets and a final target for those as well. So we are building in the ability to do technical performance measurement in this. This schedule network looks awful. It is generating too many lines, and we did not have enough time to figure that out. So it shouldn't look like this, but the concept of the critical path existing still exists. There are a lot of work products in PDR. Here, this is going to take them 38 days, and the thing's 39 days away, so there's about a 96% chance that this all gets done on time. But as you'll see in a second, this is not all of the work products that they'll have. So saying that you have a high confidence in that timeline would not necessarily be a great option. So here we're going to go to the architecture diagram for thermal control. And you can see that in the context panel over on the right, this thermal control has a couple of requirements already. It's got 3 architectural composition requirements because of its children. It's got these 3 children. You've got the requirements. It's 1-to-1 there. And then we've expressed constraints on the operational heat generation and the mass that has been defined here. So if you go to parameters, you can see the operational heat generation and the mass. We had 2 requirements for each of them, but it's only 1 parameter per se here. So we are able to attribute parameters. SysML calls them value properties, but we use parameters in system engineering. So here's the prompt. This is what this looks like. So when AOS, you can see that there's already a bunch of stuff that the user needs to do to make the model logically consistent. This is the prescription of the modeling methodology. It is deciding what to do next. And it still says description and stuff there. We got a lot of work to do. And here's the history. So when users do things, it says which queries happened in the cascade. So this is telling you what happened because of what you've done, what results did the ontology produce. So we this is kind of funny. Carlos was trying to pull the context panel out, and he couldn't quite do it. It was very funny, and you might have seen that we were doing this at 4 a.m. last night. So we've got a bunch of requirements here on those, and if we, you can see up at the top, we're going back here, we're going to the requirements panel. You see that the verification method for the architectural composition requirements, those are inspection by default. We're saying that there's not another way to do those. It should be as simple as just inspecting those. But there's no other verification methods associated with this. And on this requirements information view, this is where you can define things like requirement traceability and verification and validation kind of stuff. But here we define those as inspection, and we have inspection plan and inspection report down in these work products. So the systems engineering work that you're doing is corresponding to the project plan, the information that has to happen. Inspection plan should also be dependent on something. We don't know why it wasn't. Again, we're very, very much work in progress here. But here we're going back to thermal control, and we are going to do a couple things here. We're going to explore this one, and we've made the decision here to only show up to 2 layers on this. We just wanted to zoom in on given system elements. So we only show 2 layers. So we're going to create a composite part for this. We're going to find this is going to be plus X heater 4, assuming that we already had, 1, 2, and 3, but we're defining 4 here as a composition relationship. And so we've defined this one. You can see that the requirement populated there. The requirement is 1-to-1 with the system architecture here. So now we're going to go into the plus X heater 4, and let's give it some capabilities. Let's see what that looks like. So we go to this one. So now you can see the path up at the top is tracking what we're looking at. So it's not just that we're looking at the architecture diagram, it's the architecture diagram for this system element specifically within the path. So we go to the capabilities, and we're going to create a capability here. And this is a heater. So we're going to say that the capability is going to output heat. That's the function of it, defined in watts. And then we're not going to have an exact value. We have built in the ability to create distributions across these. So the default is the uniform distribution, but you can also express normal distribution. So you're not just saying what the high and the low values are. You can actually express what the distribution looks like in between the high and low values for Monte Carlo analysis later, which can lead us to statistical requirements compliance. So here we're going to express that the requirement minimum here is going to be 1. Requirement maximum is going to be 5. You can say the inclusive and exclusive is whether it's greater than or equal to. So it's going to be greater than 1 and greater or less than or equal to 5. And we're just assuming a uniform distribution between them. So now we have these 2 capabilities. We're going to output heat greater than 1 watt, and we're going to output heat less than or equal to 5 watts on this. We have the function output heat. It's a natural function because this doesn't own any children. The system element doesn't own any children. We've got the parameter heat. We defined 2 capabilities, but they just relate to heat. And this is where we get some of that physics-based modeling. And now we have those requirements. Again, we create the capability, and the capability requirements are defined immediately. You can also create the capability requirements, and it'll create the capability. Your system model should be 1-to-1 with your requirement specification always, and we can do that. So because we just created that capability, we've got some new prompts. You can see that in the history, the system capabilities created. It was down there at the bottom. So the prompts here, and I think we need to reverse this to make the most recent ones on top. So here we created that requirement. We need to select this verification method. So we click on the prompt, and it takes you to the information view where you're supposed to input that information. This is that modeling methodology enabled by semantic inference. So we've got this here. We go to the dashboard. We do not have the work products analysis plan and analysis report because we don't have any verification or requirements verified by analysis for this team. The team is responsible for the thermal control system element and all of its children, but there's no requirements verified by analysis. So we're going to select the verification analysis here. And then because AOS again has run those queries, so now we could say, okay, we have these work products, the history there, the verification method is selected. We know what prompts have occurred on the back end using AOS. And so then we go back to the prompts. And again, we really should make the most recent one up top, but we need to select these accountable and responsible team members. Then that's because the work products were created. If we go to the dashboard, we can see that analysis plan and analysis report have been populated. We do need to execute those, but they're not on the critical path. So they're not going to change the overall time that this team is expected to complete the work in, because that critical path, that's the path that's going to take the longest. But again, the schedule network looks terrible. We are still working on this. And also, I don't love the black and white. We can model the colors. We just didn't have enough time to do that. But I've got a couple of color schemes in mind. Anyway, so the last thing we wanted to show y'all was how the work allocation actually is going to function. So you have this new work product, and we need to select the responsible and the accountable team members. The part that we're about to show you is not hooked up to the database yet, but we wanted to show it. Here we're going to the work view. This is, and again, all this data is fake. We haven't hooked it up to the database, but this is supposed to show you all of the things that matter the most. This is the overview. We're saying these are the work products that are behind. These are the things that are most critical. This is the stuff that you should be worrying about as much as possible. And we're very much still designing this. But here we're saying what teams exist, the team members that exist, the work products and work activities that are assigned to those, and the progress that those teams are making. As far as the team members, this is where we can define, okay, we have these team members allocated to a team. Team members are giving some amount of their time to given work activities. Are we overloading them with how much time they have in the day? Who can be allocated additional work associated with it? So this is how we're able to check, team performance parameters for those managers, and we're able to see, how fast people are completing stuff, and do they have more time to help out? But all this is automatically determined. They're not updating this. It completes as a function of people inputting information into Empire. This is where you define the scheduling. If you think that work products are going to take more or less time, using optimistic, most likely, and pessimistic time estimates for the overall project timeline, and then assigning users to individual work activities. Finally, this is the responsibility assignment matrix, where you can define the responsible, accountable, consulted, and informed personnel to help figure out, okay, with the decisions that are actually being made with this, who is ultimately accountable for approving or baselining that information? Who's responsible for inputting that information? Who needs to be consulted during the compliance assessment aspect of it? So I hope that y'all can see the conjunction of project management and systems engineering enabled by the ontology layer underneath. And that was really the stuff that we wanted to hit today. And there's obviously problems with it. It's not perfect. This is pre-alpha, but we think we've got something here. We think we've got something that could potentially help a lot of people if we can just keep building ontological content into it, so that we can kind of layer it on top of each other.
Question?
Please.
So, for example, like in this example that you showed, where there's a requirement that will be verified by analysis, and so therefore EOS concludes there must be an analysis report or analysis, or analysis plan. There could be more than one requirement that will be verified by analysis, each of which needs an analysis plan, analysis report, and so on. How do you, right now I see just like analysis plan, one analysis report, but it's not entirely clear if in this dashboard view, is the analysis report for everything that needs to be analyzed, or is it is the analysis for just one of those things that need to be analyzed? And
here we're
you
doing
have like multiple reports, like, how do you, identify requirement one is analysis report one, requirements two, analysis report two, and things like this?
So first, I'll say that this is active work that we're working on with CERC right now, particularly on the verification by analysis. But what's happening here is that you've got a system element that owns a capability. And that, because that capability exists, that capability requirement exists. The thermal control team is responsible for that thermal control system element and its children. By default, you can edit that. So then when you say that system, requirement has the verification method analysis, the analysis plan and analysis report get generated for the thermal control team, because the thermal control team is responsible for that system element that owns the requirement. So we're doing a little bit of inference through multiple layers of the database there, but that's what the relational database is for. So that analysis plan and analysis report, that only exists for the thermal control team here, because they're responsible for the requirements. But what information is included in that analysis plan, that's all active work.
Maybe
But I
let me
should
ask
make
it differently. Let me ask it differently.
okay.
If we wanted to look at this analysis plan, how do you
Mhm.
find out, or do you have a way to tell, well, what needs to be analyzed in this plan?
I mean, this isn't a live demo, but if I went over here to verification and then I clicked analysis, it would take me to the information view that would say what requirements are associated with the analysis plan, what computational models or equations are being used for those, what are the analysis objectives, what are the parameters that we're looking for, how are those parameters
Okay.
going
All right.
into and out of computational models, and then the goal is if you want documentation for this, we can export that documentation. We don't want to write a project management plan or a systems engineering management plan or analysis report. All of these reports, all of these documents are just sets of linked data. So if we can put the data in here and we know what sets of linked data are associated with what work products, and then we just order those for reporting, then we could just auto generate all of the documentation.
Thank you.
Thank you. All right, so I know we're way over. I'm just going to briefly end here. We are looking to build out the community. Obviously, we have problems with how the ontology is developed. Empire and AOS are not being released open source yet. This is really just an awareness presentation that we want Empire to be on everybody's radar and to be thinking of ways that this might be improved. Because when this gets released, everybody can improve it. We are looking for people who will use this and test it and see what they like and what they don't like. So we'll get access to the repo before it gets launched. So let me know if you would like to participate in that. Software developers are the limiting reactant here. So we are looking for funding to develop purpose-driven content because there's a lot of content: integration, development, qualification, acquisition. So we're working with CERC right now on the verification by analysis for trade space analysis, and then eventually relating that to the operational concepts to say, well, okay, what's the best trade for a given operational scenario? But that's just verification by analysis. It's not verification by test or inspection or integration or development. There's a lot of specific stuff. So if you think a partnership is possible, let us know. This is a diagram for where I see all this going. Right now, we're focused on building out the core concepts. We're building out the core information and the ontological associations surrounding those. Then we're heading to project execution. What are the different life cycles that could exist? Actually developing diagrammatic con ops and ops cons. So, Nicholas, you were talking about how the concept of operations is just saying what goal-based parameters exist and what states are associated with those. Great. That's semantically linked data that can persist throughout the entire rest of the model. So when you say that certain functions or capabilities are dependent on certain states, we can start with the states that are defined in the ConOps. But on the project execution, cost and budgeting, I think is something that we could get really ingrained within Empire. It's just a matter of bandwidth here. Finally, once all that's together, we can start automatically generating a wide variety of documentation sets. We're talking ICDs, acquisition contracts, work breakdown structures. These are not things that have to be created at the beginning of the project and then disseminated to discipline engineers. These are something that just by populating a small set of information within the model, we can start building out preliminary versions of, and we have guaranteed consistency in the project plan and the system definition, which is kind of the real icing on the cake. And then once all of this is built out, we get to start things like actually building neural networks on top of this, generating functional system software directly from the models, which is something that we can already do. It's just not linked into the database yet. Determining contractual compliance between governments saying what it is they want out of a given contract and how your model is responsive to that. So actually getting government actors involved in using the models. We're able to, once we start baselining individual work products, all the work products start as not started, and then once you start adding information to it, it's automatically in progress. And then you can baseline things, which is where any changes to it have to be approved, and you can determine using the semantic inference what changes would be made if you tried to change something. But the final version is packaged. So once you package a work product, it is ready to be used in model-based reviews. So you'd be using Empire, you'd set up all these work products that you want to be shown at a given review. You set up the order in which you want to show the information artifacts, and then you just step through the model-based review. That is, I think that is certainly possible and would not be difficult once all this other content was included. Statistical requirements compliance. I mean, there's a lot of stuff where this could go here. So there's going to need to be APIs. We do want to export to SysML. We are not trying to replace SysML. We're trying to rapidly build out models and then export, because SysML will be able to do lots of things that we can't. And lots of people are going to build APIs with SysML, particularly V2. And these companies have in-house tools that they're not going to just stop using. So we need to be able to import from and export to those tools. So in conclusion, we think we've got something here. It is very early days, and we are making mistakes. We are figuring this out as we go, but I hope everyone can see the potential benefit of this in relating project management, aligning the project plans with the system definition, and reducing the effort it takes to create useful system models. Logical consistency is guaranteed as a function of the ontological utility, and we're providing a modeling methodology through the prompting of logically logically consistent information. It is very difficult to build these ontological query rules right now. We do need a better process for this. We need software engineers to translate that into TypeScript reasoner classes, and software engineers are kind of at a premium. Right now we're getting them for cheap, but also we're getting software engineers that don't really know what they're doing. But if I can teach them, I can teach people who do know what they're doing.
So,
So
I'll reach out to you because there are some nice AI code gen workflows that you could utilize here. So as a first pass of getting some code, and then you have them just review the code rather than writing it from scratch. Quite a 10x optimization at least there.
I love it. This is why we play the game, for stuff like that.
So, Michael, is it a good time? Yeah. Okay.
Yeah.
All right. I'd like to thank you so much for the inspiring talk and the great presentation and the discussion. So we are at the end of the day, and I just want to thank every speaker here, even those who went to sleep, for staying for these 2 days with us, and hopefully it was a useful event. And I would like to see more speakers next time and next year, hopefully. And I will be releasing the videos of these different sessions on the YouTube channel of OpenCaesar, and linking to them from each individual talks page. So you will have a record of this session for perpetuity, hopefully. And from my experience from last year, a lot of feedback happened after the workshop is ended than during the workshop, because it gave a lot of people exposure to these presentations. So thanks again, everyone. And that will be the conclusion of ontoNexus Forum 2025.
Thank you again, Matt.